This circuit, it's a little bit different from yours. It's pretty much the same functionality, and I did get this result 128 hertz on the output with this crystal and with this configuration. On your diagram, it wasn't clear at all that this point here should have been linked to this pin 5 or out 2 of the chip, this pin 5 out to here. So this yellow wire is this exact link, and I had quite some problems until I looked on the breadboard image that you made, and from that breadboard image I figured out this should be linked, and in the moment I link it, I got the 128, exactly 128 hertz, not fluctuating. I got a little bit confused of your markings that you had there. You had to the ground, but actually everything here is to the plus 5 volts, to the positive power, everything. And if some of them or all of them link to ground, I'm not sure yet, because I did test it and I didn't get good results from it. Then I will get 1 hertz, but no, 50 hertz I get. Okay. So I use this to 22, and that's 24. You see, it's a little bit of difference, but it's not really critical. And the junction between this resistor and that resistor here is from this point, from this line, as you can see. Okay, I used a 300 kilo instead of 330. I actually used a 220 kilo, and it didn't work well, because the 220 kilo I used it for my original experiment with the oscillator. As you can see here, this is the original with the 4060 220 kilo I used, and I also put exactly the same values that I'm having here, 10 mega and 20 kilo, and I got some results, but I mistakenly linked all these input pins, this 9, 10, 11, and 12 settings pins. I linked them to the negative rail instead of the positive, as it is correctly right now, and I was getting some fluctuating around 128 hertz. It was not stable like it is right now. So check this out. If I'm changing the division here, you should look, 10 milliseconds is right now, let's say, and so if I'm changing it to 200, you see the hertz are changing, and if I'm lowering even more, 500 milliseconds, you see it's very slow right now, and it's 28 hertz. So that's an issue I had to deal with, and now it's back to 128. But if I'm rotating it, so I was rotating it this way, and I was enlarging the division, the milliseconds, and now I'm lowering them. Now it's 50, and it's stable frequency 128, and now is 20 milliseconds, and its frequency is again stable, and now I even make it 10 milliseconds and so on, 5 to 1 millisecond, and the frequency is still constant. Is the same frequency is displaying there, and is not fluctuating at all. But let me put it like that. In my preview arrangement, in my mistake arrangement, when I link it to the ground, it was around 128. It was 133, 125, sometimes 128. But that's the the mistake that I did, and then I corrected it. But I had to read your diagram, I don't know, like more than 10 times to completely understood it, because it was vague. It's still vague on the negative. I have to test everything and figure it out. And that's it. So this pin didn't work out at all. Pin 4 is not connected to anything. But when I put this wire to it, at least in my previous experiment, here as well, is not doing anything, as you can see. So now it's on that pin 4. But when I'm switching it back to pin 5, is doing the job, which is good. It's probably some auto oscillating inside. I'm not sure, completely sure. So yeah, probably these are the outputs. This line and this line is the output from this module that we are having here, and here this is an output, but I have no idea. Probably is resonating with that one, and it's changing automatically, probably, because I did see in your diagram that you draw, and also on the datasheet, that is indeed some NOT gates, one after another. And I'm not completely sure. Probably this pin 4 is the same as the input, while this pin 5 is the opposite of the input, because of those inverter gates that is having inside. This is my suspicion. I have to look again on the actual diagram and be sure about it. Right now I'm telling from my memory, and I might be wrong, but other than that, that's it. So the output pin is pin 13 for this specific pin. The crystal is 32.768 kilohertz, or 32 kilohertz, as I like to call it, and that's it pretty much. But the first circuit that I tried it, I did made some mistakes because you have a lot of wiring, and the diagram that you made wasn't really, you know, directly like I'm drawing it, like I'm used to draw it, very direct, you know, not yeah, it wasn't, it was very very obscure what you draw there. I didn't figure it out from the first reading, not even from the 10th reading. Then after I played around here, I discovered it myself there on the breadboard, and then when I looked back, I kind of seen what you did there, but it was a very obscure hint, very obscured what you draw there. You should draw more direct, more precise, more straightforward. Not it can be, you know. Yeah, okay, that's it. We'll see if I can get it to 1 hertz, because I believe you. I believe you did got that 1 hertz, which is very important. Part 2, number 2. So what I did, I connected everything, all these pins to ground to obtain 1 hertz, and this is the result. As you can see here, it's showing 64 hertz. Okay, 63.9, 64. And as you can see, everything on my board is linked to ground. This orange wire is ground. Is the here is the ground rail inside, and here as well is inside, and outside rail is the positive as well. This outside rail is positive. So this links, all the orange links that I'm having are to the ground. The 10 kilo to the ground as well, which is this pin 15, and is there. The only positive rail link is the positive for the chip, which is the last one, the 16th, this guy here. But from here to here, 1, 2, 6, as you can see, 1, 2, and this is the 6, which is diagonal like that. And all the bits or all the inputs here on this other side, starting with 9, 10, 11, and 12, all this 4 linked to ground, and nothing. 64. Now it's actually showing 64. It was. Yeah, shit. I don't know. I have no idea how did you get that result yourself. Probably you change something else. Make the experiment again and see if you can duplicate it or replicate it. And actually show me the picture of the breadboard, and if you can make another circuit diagram and show that as well for 1 hertz, because this one worked for 128 hertz absolutely fine with the crystal, which is cool. Like you said, the chip is made for a capacitor RC connection here, not for a crystal oscillator. But this is good enough, you know. I'm very happy with the crystal oscillator. It's very precise and I like it. So yes, let's try to push it forward to 1 hertz. See what you did there that you get that result. Hopefully it's not only theoretical, it's also it's practical. All right. What I like is that it's stable. It's very, 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 very stable. It's not fluctuating at all, like the problems that I had before. Even if everything is linked to the ground right now, everything, before I was having some problems. Don't ask me why, but I did. All right. And I was getting a 50 hertz, not 64, like I'm having right now. It's a bit of probably I'm doing something right, but what? I don't know. Oh, and if I'm linking this to positive, as it should have been probably, I'm not getting anything. All right. I had to look on the datasheet itself, and and after I see the table, and I will show the table with the logic table for these inputs 9, 10, 11, 12 ABCD inputs. Also that this chip 4536 is to the power of 5, and what I actually need was power of 1 bit lower. And then I look back on the drawing of my friend from England, and he mentioned something, but I didn't quite understood it. But after I looked in the datasheet and after I seen that table, logic table, especially for these inputs, then I realized that this pin 9 it has to be to the ground, and the rest of these pins to the positive rail, except for this pin 1 and 2, also to the ground, as my friend discovered. This is his discovery, and also my friend from UK discovering is this link, I believe, yeah, this wire, this yellow wire that is coming into this output very, very strangely, but it is working. So this is his discovery, not mine. My idea, my original idea, that started all this circuit was when I was working with 4060, when I was figuring out this circuit, actually how to make it work, and especially I stay like 2 weeks only on this circuit to make it work, to understand it and how to make it work, because I didn't put probably this 20 picofarads. I didn't think they are special, but they are special, very special. And also these resistors, they were other values in other circuits that I looked, so I had to modify them. So I spent a ton of time on this crystal oscillator module only, making abstraction of the chip that is bringing down the oscillations, that is dividing the oscillations. When I was working on this and working with this 4060, this output I didn't put it here. I wonder why. But after 4060 output, I have to put a flip-flop as well. It appears I don't have the complete diagram, and it sucks. This this only remained mainly for this crystal oscillator module that I figured out how to make it work, and with the 4060. And after figuring it out to work with 4060, I had to add a flip-flop, because this 4060 is decreasing down to 2 hertz instead of 1 hertz. So I have to add another flip-flop here, only one single flip-flop that will divide that 2 hertz into 1 hertz. So it's basically it's 2 chips, 2 integrated circuits you have to add, because of this chip not being able to going too down. So you have to help its output with another chip, pretty much. So you have to add another secondary chip there. So that's the idea. This is the time when I had the idea of a single chip, like pretty much like you are seeing it here in this circuit sketch. And then I looked on internet myself. I searched for I go into Wikipedia page and looked on 70,000 series of integrated circuits and on 40,000 series of integrated circuits. And from all of those, I searched for binary counter, I believe, and then I put my eyes. I was in a sense I was lucky, and when I've seen this programmable binary counter, I actually looked here on 2 to the power of 24, and when I've seen this, I realized that is counting way over the number of times the 4060 is counting. So 4060 is limited on divisions, on the number of divisions, while 4536, this guy, is not that limited. Is having a little bit extra counting power or dividing power. And that was my idea, to use something that is counting way more many times than that 4060 or any other counter, something that is a bit more to push the dividing limit a bit more. So this was the choice that I find it. This is the choice, and this is the chip that I find it that is a bit more extra counting bits, or that was my idea. And I did received the chip, and I didn't test it at all until my friend many I believe 1 or 2 months after I received my chips, and after I made the project, and I made this project here with that counter there, with that 1 second counter that is on top of it. After he saw that side of the things that I built it, he decided to buy these guys as well, this 4536 counters, and to test them as well. And he tested them before me. Although I did have them before him, I didn't test them, and he got them way after I have them and not tested them. And he tested them, and he got the results, good results, 128 hertz and down to 1 hertz. Actually, this was a very, very important thing. If we can use one single chip to get down to 1 hertz, and we finally did it. Fucking hell. And this is it. This is the oscilloscope, and this is the frequency here, 1 hertz, exactly 1 hertz. Is the division is so 500 milliseconds per division, and I pressed like an idiot something else. And here, okay, so I put a pause to actually count everything that what is showing here. It's showing frequency 1 hertz there, and I'm supplying it as you can see 1 volt per division, and here I'm dividing per division is 500 milliseconds. So from here to here is 500 milliseconds. So one is 1 down until it's finishing up. From 1 0 until it's starting to be a 0. From 1 0 to another 0 is 1 hertz. And it's exactly what I'm having here. The LED that is blinking, I put it as a test here on this pin 13 is an LED with a resistor on it already there, and it is blinking in the same time with the rise time that is getting there. Hopefully I can catch them both. All right. Yeah, you see, when the LED is blinking, so when the LED is on, the oscilloscope is rising up, and when the LED is off, the oscilloscope is going down. Yeah, up, down, up, down, up, down, down, and so on. So it is in accordance with the oscilloscope, and it's pretty cool. It's pretty cool. I really like it. And congratulations to my friend from England, because he did discover these little tricks with the set and reset pins, where to put them. Also the logic for the input programmable pins, and this was the thing that I really liked about this counter. I never seen a counter like this with a programmable binary inputs. So until a certain value, it is counting like any other counter, and if you bypass the normal counter, it will start to count up to much higher value, like 2 to the power of 24. And you can use this select like an encoder, like a code here, and you can choose whatever the frequency you want to get, or the division that you want to get. In my case, is a division. Okay, absolutely fantastic. I really like the project, and I will make one prototype board with this chip and showing it as it is working. I will also test. Let me jump on quartz. Probably this is low. So I will show you. I will also want to test. So these are the 32, the ones that you've seen them already there. But I have this SMD versions, which is 1206 is exactly to a 1206 SMD LED size. I don't have that many, I have 20 of them. They were a bit expensive, but not very expensive. They were a tiny bit. And probably I'm curious how and if they will work, you know. And yeah, I want to test them pretty much, at least one of them, because these guys here, I did test the shit out of them, and I'm quite happy with everything that I'm having. I'm quite pleased that I get into Xtal oscillators because they are extremely precise and very stable on quite a large temperature range, if I remember right. All right, okay, get back in the cage. All right, I'm very, very satisfied, and I'm very, very pleased that it worked out in the end with 1 Hz precision counting and only one chip. And I'm very, very impressed, and I'm very, very happy, and I will probably get some more of this 4536. I hope I can find the SMD versions of them, because now when I'm having this deep packages like this, very easy to make experiments with them. Now I can jump into the SMDs, which are not so experiment friendly, and but they are they are very small sizes, and that's why I want to check those as well in the future. I'm very unexpected surprise, and very good surprise, and I'm very happy that this worked out. I have to mention that this pins that I'm having here remain the same, only this side changed. Only this side and this side changed to accommodate, to actually make it work for 1 Hz. So that's a very, very, very good thing. Excellent. Congratulations to my friend. Congratulations to myself that I was dreaming on this chip to do the right thing. I was imagining, and from imagination, from my hopes, it become a reality. But thanks to my friend as well, because he played a very good and very important part of trying it as well, and before me, and give it a serious thought, you know. And yeah, congratulations, my friend, my English UK from UK England, my friend, and yeah, good job. We will see later. But for now, this is a very good and very important progress, I believe, with only one chip. And together we realized. Well, this was a suspicion of mine that is not specified in its datasheet that is made to work with a Xtal oscillator. But this was a suspicion of mine that it might work, and it definitely did. It definitely did. So I'm not sure the maximum frequency that this can operate in range of megahertz probably, but for this 32 kilohertz is quite low, and that's why my suspicion. It was a educated guess and an educated suspicion. You know, I wasn't jumping the horse when I was believing that it might work very well with this 32 kilohertz, compared with the RC oscillator, which I'm not sure how bigger frequency. What is the bigger frequency you can get from an RC? I believe 4 megahertz, if I'm not mistaken. I believe in the peak microcontrollers they already have a 4 megahertz RC inside the chip. So this is way below a 4 megahertz. So it worked. It worked quite fine. I'm very happy about it. Yeah, this can be used as a 1 second clock for a lot of stuff, if you want to count, per second, per 1 second. All right, thank you very much for watching, and see you later with the next update. 1 Hz motherfucker, and this is constant, is not fluctuating, which is another good point. It's also stable. All right, thank you very much, and see you later with other new experience. Bye bye from your favorite artist electronics, Mr. Q12.